This is Lecture 5, Moments and Moment Generating Functions. Recall that the variance of a random variable is defined as v of y equals the expected value of y squared minus the quantity the expected value of y all squared. And note that to compute the variance, you need to compute both e of y, which is mu, and e of y squared. Now the kth moment of a random variable y is given by e of y to the k. And sometimes we'll write the kth moment as mu sub k prime. Now mu1 prime, the first moment, which is e of y, is the mean of y. And mu2 prime, the second moment, which is e of y squared, is used in the computation of the variance. Higher moments are useful as well. The quantity mu3 prime, which is e of y cubed, is sometimes used to summarize how much skewness a distribution has. And mu4 prime is used to compute a value called kurtosis, which summarizes the behavior of a distribution in its tails. Now, one way to think about moments is a series of quantities that characterize the distribution of a random variable. Think about if two random variables have the same first moments, then they have the same mean. And if two random variables have the same second moments, then they also have the same variance. And we can continue this thinking with higher moments. So it makes sense that if two random variables have the same moments, then their distributions must be the same. Okay, so depending on where you are in the calculus sequence, you may or may not have come across something called a Taylor series. Actually, we're going to look at something called a Maclaurin series, which is a special case. A function can be expressed or approximated using a Taylor series. And this states that f of x equals the summation, where n goes from 0 to infinity, of the nth derivative of x over n factorial times x to the n. Now, if we center our approximation around x equals 0, then we can write this out as f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus the third derivative at 0 times x cubed over 3 factorial and so forth. Now, one useful example of using a Maclaurin series to express a function is in the case of e to the x. We find that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial and so forth. Now let's take a look at where this comes from. Okay, so we're going to approximate f of x equals e to the x. And we have our Maclaurin series, where f of x equals f of 0 plus f prime of 0 times x plus 1 over 2 factorial f double prime of 0 times x squared plus 1 over 3 factorial f triple prime 0 times x cubed and so forth. Now, depending on where you are in the calculus series, you will know that e to the x has a derivative that is e to the x. So whether you've come across that in the calculus series or not, we're just going to write that fact down. Then we know that f prime of e to the x is just going to be e to the x. And what that means is that all further derivatives will also be e to the x. And so if we go up here and use that fact in our Maclaurin series, then what we get here is that f of x, which is e to the x, can be approximated by f of 0, which is e to the 0, plus f prime of 0, and the derivative here of e to the x is just e to the x, so this will also be e to the 0, times x, plus here we would get 1 over 2 factorial f double prime of 0, which is e to the 0, times x squared, and I think you can see the pattern from here. We get 1 over 3 factorial e to the 0, x cubed, and so forth. Now remember, e to the 0 is just equal to 1. So we can simplify this a little bit. We see that we have e to the x is equal to 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed and so forth. So now that we've seen the Maclaurin expansion of e to the x, let's take a moment to see how they are used with moment generating functions. A moment generating function is a function that spits out the moments of a random variable. The moment generating function, or MGF, of a random variable y is given by m of t equals the expected value of e to the ty. Now there is nothing particularly special about the variable t. Here we're just using t as a dummy variable. Okay, so let's think about this moment generating function. And we're going to start by just remembering that e to the x can be written using its Maclaurin expansion here. So m of t is defined to be the expected value of e to the ty. And we know by the definition that this would just be the summation of e to the ty times the probability density function p of y, and this would be summed over all possible values of y. But now let's think about expanding e to the ty using the Maclaurin expansion here. And in this case, ty would take place of the x, and remember that everything up here would then be multiplied by p of y. So this would be the summation of, let's see, we would first get 1, that's multiplied by p of y, so that would just give us a p of y. Okay, here, this would then be ty, but then that's also multiplied by p of y. And then we would get 1 over 2 factorial. This x squared, we're going to put a ty there, so that would be t squared y squared. And multiplied by p of y. 1 over 3 factorial t cubed y cubed times py, and so forth. Now summations are linear operations, so we can apply this to everything that's showing up in these parentheses here. So this would be the summation of p of y plus the summation of t y p of y plus the summation of 1 over 2 factorial t squared y squared p of y, and so forth. Now remember, these summations are over the values of y. They don't involve t, so in terms of the summation, t is like a constant, and I'm going to bring that outside. And we can also do some simplification here. Here we have the summation of p of y over all possible values of y. That's just adding up all the probabilities over all the possible values of the random variable. And we know that that's just going to be 1. Now here, let's just factor out a t. So we get t times the summation of y times p of y. Let's see, we can bring out a 1 over 2 factorial here, t squared, and then this would be the summation of y squared, p of y. Over here we could factor out a 1 over 3 factorial, t cubed, and then we have the summation of t cubed, that's y cubed, p of y. And I think that we can see that some things are popping up here. We have the summation of y times p of y over all possible values of y. Well, that's just the expected value of y. In this one right here, we have the summation of y squared times p of y over all possible values of y. But that's just the expected value of y squared. This down here would be the expected value of y cubed. So we can rewrite this as 1 plus t times the expected value of y plus 1 over 2 factorial t squared times the expected value of y squared plus 1 over 3 factorial t cubed times the expected value of y cubed, and so forth. And if we want to use our notation for moments, we can rewrite this as 1 plus mu 1 prime times t plus 1 over 2 factorial mu 2 prime times t squared plus 1 over 3 factorial mu 3 prime t cubed, and so forth. Well, now let's think about what would happen if we go in here and we take the derivative of the moment generating function. Okay, so the first derivative, L prime of t, let's see, this would just be a constant. This is a constant times t, which would just give us mu 1 prime. And then we have, let's see over here, the 2 would come out in front, cancel with the 1 over 2 factorial. It looks like we would be left with mu 2 prime t. Over here, the 3 comes out in front. Remember, this is 1 over 3 factorial, so that's actually 1 over 3 times 2 times 1, and that 3 would cancel with the 3 down here, leaving us with a 1 over 2 factorial mu 3 prime times t squared, and so forth. All right, the second derivative, I think you can see that this would just be 0. That's just a constant. Looks like we would get mu2 prime. Over here, let's see, this 2 would cancel with this 1 over 2 factorial, just leaving us with mu3 prime t plus other stuff. I think you can see that the third derivative here would just be mu3 prime plus other terms, and all those other terms would involve some value of t. And it's pretty easy to see straight from here that if I were to look at m prime of 0, all of these values up here that involve t would just go away. I would be left with the first moment, mu1 prime. M double prime of 0, well, let's see, I would get this one, and everything else out here that involves t would just be 0. Looks like that would just give us the second moment, mu2 prime. The third derivative at 0 would just give us mu3 prime. And I think you can see from there the pattern. And so what we just demonstrated is that if we let m of t be the moment generating function of a random variable y, then the kth moment, mu sub k prime, is given by the kth derivative of m of t, where t is set equal to 0. So let's look at an example. A random variable y has a moment generating function m of t equals 1/4 plus 1/2 e to the t plus 1/4 e to the 2t, and we want to find the mean and variance of y. So we've got a random variable, and we know the moment generating function is m of t equals 1/4 plus 1/2 e to the t plus 1/4 e to the 2t, and we want to find the mean and variance. Well, we know that the mean and variance are found using the first and second moments. And so let's go in here and find m prime. And it looks like what we get here is, okay, that goes away. It looks like we just get 1/2. Remember, the derivative of e to the t is just e to the t. And over here, we're going to get a 1/4. The derivative of e to the 2t, now we're going to have to use the chain rule here. The outside derivative would just give us e to the 2t. But the chain rule says you got to multiply by the derivative of the inside function, which gives us an extra 2. And so it looks like what we get here for the first derivative is 1/2 e to the t plus 1/2 e to the 2t. And we might as well go ahead and find the first moment, which is just the expected value. So the first moment is m prime of 0. And it looks like we would just get 1/2 e to the 0 plus 1/2 e to the 0. That's just going to be 1/2 plus 1/2, which equals 1. And remember, this is your expected value, which is the mean. Okay, to find the variance, we're going to need the second moment. So let's find the second derivative. Okay, let's see. The derivative here, okay, we get 1/2 e to the t. The derivative there would just be 1/2 e to the t. Over here, we get 1/2 e to the 2t, so I'm going to leave my 1/2 there. Derivative of the outside function gives me e to the 2t. Chain rule tells me I get an extra 2. And so it looks like what I get is 1/2 e to the t plus e to the 2t. And so the second moment is m double prime of 0. And I think you can see from here that that would just give us 1/2 plus 1, which is 3/2. The variance of y is the expected value of y squared minus the expected value of y quantity squared. And if we write that in terms of moments, that means that we have mu2 prime minus mu1 prime squared. And that's going to give us 3/2 minus 1 squared. Looks like we get 1/2 as the variance. So why do we care about moment generating functions? Well, first of all, moment generating functions create a bridge between the subject of calculus and probability distributions. which allows us to use all the tools of calculus in our study of distributions. Also, if two random variables x and y have the same moment generating function, and hence the same moments, then x and y are distributed the same way. Another point is that if we know that two random variables x and y are independent, then the moment generating function of the new random variable x plus y is the product of the moment generating functions of x and y. And this will be a useful fact when we start thinking about transformations of distributions. Now, it may not be apparent why the moment generating function of x plus y would be the product of the moment generating functions of x and y. So let's take a look and see how this works. So we start off assuming x and y are independent. Now the quantity x plus y would be a new random variable. So we're going to look at the moment generating function of x plus y. And we know that would be the expected value of e to the t times x plus y. Well, just multiplying the t inside the parentheses, we can write this as the expected value of e to the tx plus ty. And then using the properties of exponents, this is the same as the expected value of e to the tx times e to the ty. And here we use the fact that x and y are independent because we can now write this down as the product of two expected values, which is the expected value of e to the tx times the expected value of e to the ty. But this would then just be the moment generating function of x times the moment generating function of y, which is what we're trying to show.